Okay, so we're going to start our semester in biochemistry studying chemical bonds. Now this topic is really a review for you, so there's no real new information here. This should be stuff you've learned about in some of your other classes. So I'm going to kind of roll through this and just kind of mention some of the key things you need to know about chemical bonds from your previous classes, so kind of highlight some of the important things from your other classes that you need to know. Before I get into that, let me just a few announcements and reminders for you. One is the syllabus has been posted. It's a preliminary syllabus, so if you think there's something in there that doesn't seem right to you, it's confusing to you, please let me know, because I can update that syllabus and we can make some changes to it at this time for this week. And so I want to try to solidify something by Friday or Monday of next week for sure. But again, this syllabus is tentative as long as we stay in class and have the in-class hybrid section. If we ever do happen to go online through the semester and that the university shuts it down and we go online, everyone will go over to the 100% online portion. But at this point, I'm going forward as though that's not going to happen, and we're going to have it the way we have it, a hybrid option and an online option. In regards to that, make sure you've taken the survey. The highest significant amount of you have taken that survey. Thank you for that. But I need the rest of you to finish that survey up. Otherwise, I'm just going to have to assign you to one of them. In regards to that, the survey is closing on Friday at 5 o'clock, I think is what it's set at. After that, I will be, the ones of you who have chosen the hybrid option, I'll be sending you emails to let you know what day next week that you are, a seat is available for you in class. Remember, we all can't just come on Monday to the in-person meeting because there's not enough seats. So I got to section you guys off. So once I figure out who that student pool is that wants to do the hybrid part, I will send an email and you will get that email over the weekend. So be prepared to go to class. Some of you will be going to the in-person class on Monday. Some will go on Wednesday and so forth. And the third thing to note here is our first 9:30 quiz is on Friday. It'll be over lecture 2, which is the one I'm giving right now, and what I'll get into. So it's basically a review 1, and this one's just to kind of get you into the swing of the 9:30 quizzes and how they'll run. It should be pretty straightforward on Friday. It will be online, so do check in at 9:30 and go ahead and take it. It will be timed. The questions will come up and you won't be able to go back to the previous question once you answer one and submit it and move on to the next question. And this is in an effort to kind of get you, especially you online, 100% online students, to kind of get you into the mode of, hey, exams are going to be timed, quizzes are going to be timed, and we got to get used to that. So this kind of gets you all prepared for that as well. But again, the major point of this 9:30 quiz is to keep you up on the topics so you're not falling behind. So when exam day comes, you're not 10 lectures behind, that we're going to kind of give you some motivation to keep up with that. I expect you all to do very well on these quizzes. Again, these are more to kind of, are you keeping up and watching the videos? So let's get into chemical bonding. And there's really two major types of bonds that we're going to be talking about. One is covalent bonds, and the second category is non-covalent bonds. And non-covalent bonds we can even further subdivide into 4 different types. And those are electrostatic interactions, hydrogen bonds, van der Waals interactions, and hydrophobic interactions. And I'm going to go through each of these individually in this lecture, so we're going to hit all these in this lecture. So this is basically the outline for the lecture today, is that we're going to be studying bonds. So covalent bonds are the ones that you are probably very familiar with. These are the ones that we first learned about probably in general chemistry. And these are the ones in organic chemistry where you drew the lines in between 2 atoms. So for instance, down here we have a line in glycine between these 2 carbons. That is a covalent bond. It's a solid line that connects them. Sometimes that line is not shown in a compact formula. We get more covalent bonds over here. Notice benzene has some double bond character to it. It's not a true double bond, but it nevertheless has some double bond character to it. But those lines are representing what is a covalent bond. And this is a bond in which electrons are being shared between the two atoms that are connected by that bond. It turns out that double and triple bonds are shorter. Double bonds are shorter than a single bond, and triple bonds are shorter than a double bond when we have those between two, when we're comparing bonds that have the same atoms that are being connected. So if we use carbons as an example, a carbon-carbon single bond is longer and weaker than a carbon-carbon double bond, and we can move that onto a triple bond. Resonance of double bond makes them even stronger, and when we're talking about stronger, we're really talking about stability in many ways. So it's harder to break bonds that are stronger, and so therefore it stabilizes that structure. When reactions happen, it's harder to break bonds that have resonance structure. Benzene's a wonderful example of that, where there's plenty of resonance structure in there, and benzene's a difficult molecule to break those bonds, and reactions really don't break those bonds well unless you use very, very harsh conditions. To exemplify this in a graph form that's shown here, you can see here that if we look at a single carbon-carbon bond, you can see the length of the bond in angstroms is 1.54. If we compare that to a carbon-carbon double bond on the lower row, you can see that the length of that bond gets a little bit shorter. Notice the energy are also very different. A single bond has 356 kilojoules per mole, while a double bond has 730 kilojoules per mole in them. You don't have to memorize those numbers at all. Again, this was just to solidify our understanding that as the number of bonds between two atoms increases, the length decreases and the energy increases. So covalent bonds are great. We're going to see them in structures as we study those. We'll see them in proteins and lipids and carbohydrates. And when we see reactions with those molecules, we'll be breaking covalent bonds and making new covalent bonds, similar to things you saw probably in organic chemistry, except we'll be using molecules of living systems only. We're going to focus on those. Non-covalent bonds are also very important. Now, they're different from covalent bonds because they don't share electrons. So this is not a sharing of electrons anymore. These bonds have much different types of interactions. Some of them are electrostatic, some of them are hydrophobic, and so forth. These most often depend on the attraction between opposite electrical charges. So you all know that if you have a positively charged ion and a negatively charged ion, there's an attraction between those two ions. Positive and negative opposite charges attract. Similarly, like charges repel each other, and the stronger those charges are, the greater the repulsion. Much like the stronger the charges are that are opposite, the greater the attraction. But these are much weaker bonds than covalent bonds. They can be in the order of 10 to 100 times weaker. And so you might be wondering, well, if they're so weak, why do we even care about them? Why do they do anything? And in biological systems, we're going to see a lot of importance of these. We're going to talk about non-covalent bonds all semester long. So this isn't going to go away, and this is why I'm bringing it up in this initial lecture about things you should already know. And that's because, and I'm highlighting this, and that's because we're going to see it a lot. Why are they important? Well, they actually are the ones that help determine the structure, or at least they're one element to determining the structure of proteins, of membranes, of nucleic acids. Many of you might know already that the DNA is a double helix. Well, that double helix structure is in many ways not only formed by covalent bonds, but non-covalent forces really set that structure up and give it that helical shape. It's also responsible for associations within molecules, as in the DNA double helix, and between molecules. So if you have multiple molecules interacting, especially in a transient way, in a way that is not going to last for eternity, but in a way that's sort of a temporary, where the interaction needs to occur for a biological process, and then that interaction needs to stop over time, that's almost always going to be a non-covalent interaction between the two. And so these non-covalent bonds, these non-covalent forces are very, very important in biological systems. And we're going to see that a lot, and we're going to have plenty of examples of this throughout the semester. So let's take a look at these 4 different types of non-covalent bonds. Again, you should always already be somewhat familiar with them. And the first one is electrostatic interactions. And this is really just a pretty simple, we have one positive charge and one negative charge, and they can attract each other because positive and negatives opposites attract, where if they're the same charge, they repulse each other. And we can calculate the force, or the attractive force or the repulsive force between these two ions using what's called Coulomb's law. And there's a little bit of an equation for that we can do that, where E is the energy of attraction or repulsion depending on whether the charges are the same. Q1 and Q2 are the charges. So if Q1 was a positive charge and Q2 was a negative charge, that would be an interaction where those two are going to be attracting each other. And based on their distance apart from each other, we can calculate how much energy is occurring between those and how much pull together are they. If you think about, and that distance is important, and let me give you an example of why that distance is important. You've had this experience in life before. Take 2 magnets, or even just take a magnet that you're trying to put on the refrigerator. If you're holding that magnet 1 foot away from the refrigerator, or at a pretty good distance, and you let go of the magnet, we all know it's just going to fall to the floor. The reason is because the force of gravity is greater than the attractive force between the magnet and the metal refrigerator. But if you got that magnet closer and closer to the refrigerator, there would be a point at which you could let go of the magnet, if it was a strong enough one, and it would jump to the refrigerator. Maybe a different way to put this is take a positive or 2 poles of a magnet, and you try to bring them together where one's positive, the positive pole, and one's the negative pole. And as you bring those 2 magnets together, there comes a point where all of a sudden they'll snap, and the 2 magnets will come together and hang on to each other. And when you try to pull those apart, initially it might be very difficult to pull those apart, but as the distance between the 2 magnets gets greater, it becomes much easier. And that's this R distance. So the force changes based on how close those 2 charges are. If you think about proteins as, and we'll get into proteins, but if you think about a protein or a molecule, as positive and negative charges within the molecule or between molecules get closer, those could cause those 2 molecules to come together better if they were closer at a certain time and place in the cell. K is just a proportionality constant, so that's just a number that's given for the equation. And D has to do with what kind of solution is it in. It's called the dielectric constant, and so it depends on whether is it in water, is it in oil, is it in an alkane, like hexane or something like that. So depending on the medium that it's in, or the solution that it's in, or the solvent, I should say, it will vary the value of D. So this next one I want to talk about is polar bonds. And if you look at this molecule here, this is a molecule of water. The question might be, are any of these bonds polar? And what do we mean by polar bonds? Well, polar bonds are basically partial charges. So if we think about NaCl, for instance, there's Na, the sodium, is positively charged, and Cl minus if we draw it with the charges on them. And those are full charges. That's an Na plus. If you don't have the number next to it, it means +1, and Cl -1. And so those have full-on positive. Sodium has a full-on +1 charge, and chlorine has a full-on -1 charge. In a polar bond, and what that means is that electrons were transferred from one of the atoms to the other. And in this case, sodium gave up one of its electrons to chlorine, and chlorine accepted that electron, so therefore it got a -1 because electrons are negatively charged. And since sodium lost an electron, it becomes positively charged. In a polar bond, it's an unequal sharing of electrons. So yes, we do have a covalent bond between that oxygen and that hydrogen. But that oxygen and that hydrogen are not sharing those electrons equally. This might be if you went on a date, and now it would have to be before COVID. But if you went on a date and you were going to go to the movie theater with your date and you ordered a bucket of popcorn. Of course, you're on a date, so you only order one bucket of popcorn, right? And you put it between you two at the movie theater, and you're eating them, and you're at the movie theater. The thought is maybe you get half of the popcorn, so it's an equal sharing of the popcorn. You get half, and the person you're with gets half. But we all know many times that we don't get half of the popcorn in that situation, that the person that we're with might eat more of the popcorn, or maybe we're the person that's eating more of that popcorn. So it's an unequal sharing of the popcorn. That's what a polar bond is. A polar bond is one in which those electrons are not being shared equally. And so therefore one of them will get more than the other. If it gets more popcorn than the other, or in this case more electrons than the other, it'll be partially, it'll be partially negative. So in this case, oxygen will be partially negative. And hydrogen, who didn't get quite as much of the electrons, will be partially positive. So these aren't full, hydrogen doesn't have a full +1 charge like sodium does, because it's not getting all of the giving up all the electrons. It's actually just giving up some of them. So it's giving up a little bit of electrons, and oxygen's getting a little bit of electrons. So a partial negative charge is not quite as strong of a charge as a full-on negative charge that we see with chlorine. It didn't get all, chlorine got all of the electrons. Chlorine would be like if you went to the movie theater and you were there with somebody and you got no popcorn, the other person ate it all. So in this case with sodium and chloride, chlorine ate all of the popcorn. It got all of the electrons. In this case, maybe the oxygen got 75% of the popcorn and hydrogen got 25%. So the amount of electrons, so electrons tend to be more hovered around the oxygen and less around the hydrogen. This is called a polar bond. And you can see why this is important, because we have sort of a charge on there. Maybe it's like a negative 0.5 charge and hydrogen's a positive 0.5 charge. Now we don't go and give numbers based on those atoms and that unequal sharing of electrons so much. We just say that there's a polar bond there. If you had a bond, let's say in methane, if we looked at methane for just a moment, or actually let me look at ethane, and we have ethane there, and we all know that there's a bunch of hydrogens around these carbons. Whoops. Sorry, I'm a little bit jammed up here at the top. But let's look at the bond, the covalent bond between the two carbons. So I'm referring to the, with the purple arrow here, that's pointing to that bond between the two carbons. Because they're both carbons, they're going to actually share electrons perfectly equally. So that wouldn't be a polar bond. That would just be a standard covalent bond. This bond over here, this with the hydrogen and oxygen, that's also a covalent bond, but it's a polar covalent bond, where the carbon-carbon bond is just a covalent bond. Now, how would I know that two electrons or two atoms don't share electrons or do share electrons equally? And for that, we bring in the electronegativity chart. That's all that chart tells you. That chart will tell you who shares electrons and who gets most of the electrons when they share. So let's do some calculations here for just a moment so we can figure that out. Let's take this oxygen-hydrogen bond. What we do is we look at the atoms from each of those on the periodic table down here. So I have oxygen down here, and I have hydrogen over here, and notice there's a value with those numbers. Now don't worry what the actual value is. We're not going to get into why is oxygen 3.5 and hydrogen 2.1. Don't worry about that. All we care about is we need to be able to grab those numbers. So let's look at this bond. So it's a bond between oxygen and hydrogen. Oxygen, I'm going to write it up here. Here's oxygen and hydrogen. Oxygen is 3.5 and hydrogen is 2.1. If I subtract those, I get 1.4. So the difference between those two numbers is 1.4. If the number, when you subtract them, is greater, where can I write this? Is greater than 0.5, it is a polar bond. Unless, of course, it's greater than 1.6, then it is an ionic bond. That's where one atom gets it all and the other one doesn't get any. Remember sodium chloride. If it's equal to or less than 0.5, it is considered just a standard covalent bond. And sorry, my writing is very bad. Oops, less than or equal to 0.5. Okay, so in this case, our 1.4 falls in the area of polar bond. So that tells us one thing. The other thing we can learn from this is the one with the bigger number, in this case the oxygen, that's the one that gets most of the electrons. That's the one, and since it's getting most of the electrons, it's the one that's partially negative. If we take this one step further, let me just erase some of these marks so we can get some more space. Whoops, I didn't want to go that far. Ionic bond right there. And we had less than or equal to 0.5 was just a covalent bond. Again, a polar bond is still a covalent bond. It's just a polar covalent bond. I've sort of abbreviated that in the chart here. So this chart is important to know because that one will help you. So let's look at a carbon-carbon bond. If we look at a carbon-carbon bond, carbon has a number of 2.5 on our electronegativity chart. 2.5 minus 2.5 is 0, and 0 means it's a covalent bond. Okay? And a covalent bond basically means where it's a non-polar, or we can call it a non-polar bond. So it's a non-polar covalent bond. So a non-polar bond is one in which the two atoms are equally sharing the electrons. Another big one we see in biochemistry is carbon-hydrogen bonds. Carbon has a 2.5 on the chart. Hydrogen has a 2.1 on the chart. We subtract those from each other. We get 0.4. 0.4 on our little chart over here, again, is a non-polar covalent bond. And so non-polar bond means basically the two atoms are equally sharing, and therefore there's no partial charges on those atoms. And it's those charges that we're really interested in. And for our last one, to show you an example of an ionic bond, we can take an NaCl. Na over here is 0.9. Chlorine is 3.0. We don't worry about it being negative. We just say 3.0 minus 0.9 equals 2.1. And you can see there 2.1 is definitely an ionic bond. You went to the movie theater with someone who basically ate all the popcorn and you got none. That's an ionic bond, and those guys will have full charges, a -1 for the chlorine and a +1 for the sodium, because all of the electrons went to chlorine. So those are how you would use the chart. So an electronegativity chart is really cool for us. It can tell us if any of those atoms have charges in the molecule. So let's take a look at now what van der Waals forces are. Van der Waals forces are forces between neutral atoms. Okay, so these are atoms that don't have, when you look at them, they don't have any charges. An example might be like methane or any alkane. You know, if you look at those structures, you'll see that there's no charges on them. You don't look at those and see charges. Not like sodium chloride where we see charges. These are forces that are occurring between neutral atoms. So these are atoms that don't have any charge to them at all. At least full charges, we should say. And this occurs between atoms with a permanent or induced dipole. These play a larger role with nonpolar molecules, and these are weaker than electrostatic interactions. So a positive-negative charge interaction is pretty strong in terms of non-covalent bonds. These guys are a little bit weaker, and you can see here that if we look at this molecule here, you see that, notice carbon-oxygen bond that we have here in this molecule. So this is a big molecule, and part of it has this carbon-oxygen double bond. You can see here in that bond that If we go back to the electronegativity chart, we'll find out that that's a polar bond, and so oxygen has a partial negative charge and carbon has a partial positive charge. That gives this molecule a little bit of negative character on one side and a little bit of positive character on the other. If you interact it with another the exact same molecule, and you put two of them together, the molecules will orient themselves so that the positive and negative partial charges are closer together and are attractive to each other. If we flip this molecule around, this one, you would then have two negative charges near each other and they would repulse each other. So these dipole-dipole moments will sort of organize the molecules in such a way that there's some attractive forces between them, not repulsive. And these dipole-dipole are due to these polar bonds that we just talked about. So we'll see those a lot of times in these polar bonds. And we call those permanent dipoles because those polar bonds will always be there. They never disappear. When you have a carbon-oxygen double bonded in a molecule, the carbon will always have a partial positive charge and the oxygen will always have a partial negative charge. Another interaction we'll see is when we have a dipole versus interacting with an induced dipole. So again, in our dipole molecule, it has a polar bond in the molecule. So one of the atoms has partial negative charge, one has a partial positive charge. And in the other molecule, it's a molecule that has no polar bonds. So in this case, they're showing methane. So methane, of course, has this structure. It has four covalent bonds. And if you looked at the electronegativity chart, and we did this already, I believe, with carbon and hydrogen, you'll see that there's no polar bonds. All four of these bonds are nonpolar, so therefore there's no partial negative charge anywhere in this molecule, no partial positive charge. This is a nonpolar molecule because all of the bonds are nonpolar. And therefore it doesn't have what you wouldn't think it would have a negative charge to it at all or a positive charge to it all, not even a partial one, because it's nonpolar, and that is true. Except that an induced dipole is one in which the first molecule with the partial negative charge near the other neutral or nonpolar molecule induces a dipole. It forms a temporary positive charge on one side of the molecule over here and forces all the electrons over to this side. So this negative charge scares essentially all the electrons in this molecule to move to one side temporarily. Remember, electrons are moving around. They're flying around all the atoms, right, in a huge space. So it's really electrons that are forming the molecular structure, at least on the edges. And so if you bring a negative a charge near a molecule, a lot of the electrons will move to the other side of the molecule. And so this is what happens, and we call that an induced dipole because the first molecule induced a dipole in the other molecule. Notice now this molecule has a partial negative charge on one side and a partial positive charge on the other. But if this molecule were to disappear and leave the area, this induced dipole would disappear and the molecule would just be nonpolar, no charge to it at all, because the electrons would be evenly distributed through the molecule. So what this molecule does, the first molecule does with the polar bond, it forces charges to move into certain spots and locations in the other molecule. So therefore, the dipole that was made was induced by the first molecule. And then the last one is what we call induced dipole interactions. This is where we have two neutral molecules. And so you'd think, well, how can you make charges move around or onto one side of the molecule? So I mentioned before that these electrons are flying around. And we like to think that these molecules are flying around in a way that's very uniform, where they're all spread out evenly. They're socially distancing themselves from each other. But in actuality, I like to think of electrons flying around in a molecule more like watching kids in a swimming pool. So if you go to the community swimming pool and you have a bunch of kids in the water, you would think that they would mostly separate from each other and spread out. But if you're watching, there might be a point in time where all the kids have just by chance, not that they're all hanging out together, by chance are all of a sudden just on one side of the pool. and the other side of the pool looks pretty open, that there's no kids over there for a brief moment. And if you watch a little bit longer, eventually some of the kids will straggle back down to the other end. But they're not evenly distributed through the molecule. And so that's what this is referring to, that these electrons flying around, there might be a point in time where a lot of the electrons in this first molecule here that I'm squaring swim onto one side of the molecule, leaving no electrons on the other side. Because now you have this negative charge that has temporarily formed on this side of the molecule, it will induce a dipole in the other molecule, forcing all the electrons in this molecule to kind of move over to this side of the molecule in a repulsive way. And so temporarily, we'll have this induced dipole interaction in the molecule. All molecules can do this, even if they're nonpolar. All molecules, but it's temporary. It doesn't last forever, because eventually these electrons will swim back over to the other side, make this molecule with no dipole, and now this interaction between these two is lost, and it goes away. So these are kind of coming, these are always going to be happening. Electrons will eventually end up on one side of the molecule, and it'll cause changes to a nearby molecule, because all of a sudden you have this huge electric negative field in one part of the molecule. Now, a specialized dipole-dipole interaction that we'll be talking an awful lot about in this semester is hydrogen bonds. So these specifically only form in a couple of ways. You must have a nitrogen-hydrogen covalent bond in a molecule, or an oxygen-hydrogen bond in the molecule. If you do not have either of those bonds, hydrogen bonds cannot form. You must have at least one of those two. So if you look at an alkane like methane or ethane, where you have just carbon-hydrogen bonds and carbon-carbon bonds, notice they can't form hydrogen bonds. Are there hydrogens in ethane? Of course. There's a lot of hydrogens in ethane. So here's the structure of ethane. Notice we have plenty of hydrogens. So just because you see a hydrogen doesn't mean it can form a hydrogen bond, because I don't see anywhere in this molecule a nitrogen-hydrogen bond or an oxygen-hydrogen bond. If you don't have one of those, you can't form a hydrogen bond. So this molecule, and all alkanes for that matter, can't form a hydrogen bond. But if you do have a nitrogen-hydrogen or oxygen-hydrogen, it has the potential to form a hydrogen bond. So why does this work? Well, partly, now if we go back and look at our electronegativity chart, we can see that nitrogen would grab more of the electrons than hydrogen, and therefore would be partially negatively charged, as shown here on the slide. Hydrogen, therefore, would have a partial positive charge. If it interacted with another nitrogen, or could interact with another nitrogen, now we could think about this one being bound to another hydrogen, and so it also forms this partial positive, partial negative polar bond. You can see that now you have a partial positive charge, and it would be attractive to the partial negative charge of the nitrogen on a different part of the same molecule, or it could be a completely different molecule. It doesn't really matter. And so therefore, that can form what's called a hydrogen bond. The green dashes you see between the hydrogen and nitrogen, or the hydrogen and the oxygen you see down in a couple other examples, that green dot is showing the hydrogen bond. So anytime you see these dashed lines between two atoms, and then there's a hydrogen involved and a nitrogen, or a hydrogen and an oxygen, that's typically representing a hydrogen bond. Again, these bonds are much weaker than the covalent bond between nitrogen and hydrogen, right? Notice they're also, which is very important in this picture, notice they are much longer. Look how much longer the distance between that hydrogen and the oxygen is versus the hydrogen and the nitrogen here. Okay, so that's what a hydrogen bond is. So again, when you're looking at, the question comes up about, does this molecule, can this molecule form hydrogen bonds? You're looking for, all it's really asking you is, can you find an oxygen-hydrogen bond or a nitrogen-hydrogen bond? Okay, that's what you're looking for. And that will tell you if that molecule has the potential to form a hydrogen bond. Just a couple notes and more specifics about it, and kind of highlight some of the things I may have just said. Notice, first of all, the distance between the atoms. In a covalent bond between nitrogen and hydrogen, the distance between them is 0.9 angstroms. The hydrogen bond, notice, is much longer. If those two bonds are are basically on a straight line with each other, like it is shown here. Notice I can draw a straight line between all three of the atoms. That creates the strongest hydrogen bond possible. And so if a molecule wants to form a strong hydrogen bond, again, a hydrogen bond is still weaker than a covalent bond, but nonetheless, if it wants to form a strong hydrogen bond, it tries to get those three atoms lined up on a straight line. And that's what's mentioned down here in part 4. If it's not on a straight line, and it's more like this, where you have oxygen, hydrogen, and its hydrogen bond goes down to a nitrogen, notice these three atoms are not along the same line, and therefore this would be a much weaker hydrogen bond than this hydrogen bond up here. And so we can learn a little bit about the strength of a hydrogen bond, and later down in the semester we'll be talking about this and how enzymes can use this feature to strengthen the interaction between two molecules. And the last one I want to talk about is the hydrophobic effect. The hydrophobic effect is another very important one in biochemistry. You'll be hearing about this all semester long. And what this is the aggregation of nonpolar molecules in water. What I mean by that is, if you think about oil and water, everyone knows that oil and water do not mix. And that can be a beneficial thing for us, because when there's oil spills in waters, it's good that the oil doesn't mix with the water perfectly, or else we'd have to filter the ocean during an oil spill. It turns out that the oil rises to the top of the water, and the cleanup procedure, it typically involves skimming the oil off the top of the water, because oil and water don't mix. If I were to take a bottle and I would put water in it and oil in it, we would see two layers. They wouldn't mix very well at all. We'd have water typically on the bottom. It depends on the density of the oil that you're using, but water would sometimes be on the bottom, and if it's a low density oil, it would rise to the top. And we'd look at it and we'd see two layers. And I could sit there and I could take that bottle and I'd shake it like crazy, and then I'd let it sit on the counter. And what happens? The oil rises back to the top and the water goes back down underneath it. And that's just amazing, right? That sounds to me like if you took your clothes out of the dryer and you threw them up in the air and they landed on your bed folded and neatly stacked. The hydrophobic effect is amazing. When I shake this bottle up, it separates into two perfect layers. I don't have to plug the bottle in. I don't need to add batteries. I don't have to do anything special. It just separates beautifully into two layers. How can this be? Because we all know that when we're in the world, things tend to look more disordered through time. So why does this happen? So here's a representation of what I'm referring to. If I shake up the bottle, which is shown here in the first one, there's a bunch of little nonpolar molecules, the oil, just floating around independently in the water. As I sit there and watch the bottle reform the two layers, what's actually happening are these little droplets of nonpolar molecules start to coalesce and come together. And the more of those that come together, the more the oil becomes more uniform, and because this oil is less dense, it rises to the top, and we end up with a beaker with water on the bottom, oil on the top, and we have two beautiful layers. So the question becomes, why does this occur? And it occurs from one major thing you've heard about since general chemistry. If you took physics, I'm sure you heard about it in physics. You probably heard about it in organic chemistry, and now you're hearing about it again. This is the second law of thermodynamics. That is why this happens. During a spontaneous process, the total entropy of a system and its surroundings always increases. Wait, what? The entropy always increases. But wait a minute, entropy is disorder. So this is saying that disorder is going to increase in this system. But when I shake up a bottle, that's the most disordered it gets. It gets ordered over time. I get two layers. It seems to order itself very well. It's like organizing itself. This seems to be not increasing entropy. This seems to be decreasing energy, and that goes completely against the second law of thermodynamics. Dr. Rule, what in the heck are you talking about? What I'm talking about is this, is that if you look at nonpolar molecules, when we shake up the bottle, and I see them here, I have in this image over here, there's two nonpolar molecules that have been separated from each other. They were originally one layer, and now they've been separated from each other. When those two nonpolar molecules are in the water, water itself forms a cage around this nonpolar molecule. I don't think this image does a great job of showing the cage, but the cage is a very ordered way the water forms around the nonpolar molecule. And so it's forming a beautiful cage around this nonpolar molecule, a very ordered cage. And it's forming a very ordered cage around this molecule and all the other nonpolar molecules that had been separated due to the shaking that I did. As the molecule, after I stop shaking and these nonpolar molecules start coming together, the number of molecules of water that must form this cage decreases. So there's still some water molecules very ordered forming this cage. But there's also a lot of other water molecules that were forming the cage earlier, but are no longer needed to form the cage because, well, when you start bringing nonpolar molecules together, the area around them becomes less. And so notice it's becoming more disordered because these water molecules have been freed. And so they're not needed to be very ordered anymore. So although when we shake up a bottle of oil and water, to our eyes it looks more disordered, at the molecular level it is very ordered when you shake up when you have this condition. This is a very ordered system. As we allow the two layers to form, it gets more disordered. Yes, not to our eyes, but at the molecular level, way more disordered. So the hydrophobic effect is a very important one. What this means to us in biochemistry is nonpolar molecules are going to want to hang out with nonpolar molecules. Why? Because the hydrophobic effect. Notice in this case, the two nonpolar over on the left, the two nonpolar molecules are apart from each other. They're not together. They don't like that. They'd much rather be together. So when we see things that are nonpolar, we'll start seeing them come together, get closer together, and be more happy to do that in biological systems. Remember, in biological systems, our cells, plant cells, cow cells, they are mostly water. And so the environment for a nonpolar molecule is not to be separated from other nonpolar molecules, it's to be together with other molecules. So that is the review that I wanted to give you. Here is from the first lecture. We're on lecture 2. Lecture 1 was the introductory lecture. There's no slides to post there, so that's why on Canvas we started with lecture 2, because I don't have PowerPoint slides for lecture 1, but this is actually lecture 2. And here's some of the things we need to look at. Do check and get some information. Make sure you're starting to look at those organic functional groups. I'm going to be starting to talk about those right away, so you definitely want to do that. We did do a little bit about thermodynamics. We didn't cover them all, but there's a little bit more there. Chemical bonding, we pretty much hit all that here for sure, but there's definitely some other things to look at as you're preparing yourself for the subsequent lectures coming up. So with that, I'm going to stop. That's the end of lecture 2. And we will now start in lecture 3. We're going to start with amino acids and the new topic, and we're going to get into a new topic starting in the next lecture.